So let's just jump right in with a question that, trips up a lot of people when they're first getting into electronics. It's a real head-scratcher. Are Kirchhoffs laws wrong?
And you can kind of see where the confusion comes from, right? You picture a circuit, the current splits, and maybe one path is way harder to get through. So do some electrons get stuck? Or what about energy? If a battery gives a bigger push than the circuit seems to need, where does that extra juice go? It can feel like these simple rules are starting to fall apart.
But here's the thing. The laws themselves, they don't actually break. The solution to this whole puzzle comes from a couple of beautifully simple rules that were figured out way back in the 1840s.
And these rules, which are the absolute bedrock of analyzing circuits, they came from the mind of a German physicist named Gustav Kirchhoff. This is a man who really helped to lay the foundation for all of modern electrical engineering.
What's just wild is that Kirchhoff came up with his famous circuit laws in 1845 while he was still a student. Can you believe that? And then he goes on to team up with Robert Bunsen, yep, that Bunsen burner guy, to completely change the field of spectroscopy. The man was a true giant in physics.
So, let's start with his first law, which is all about current. This is the one that solves that whole lost electrons problem we started with. And really, it's just a simple statement about a fundamental law of the universe, the conservation of charge. The main idea? Nothing gets lost.
Okay, so the textbook definition is Kirchhoff's current law, or KCL for short. And all it really says is that at any point where wires meet in a circuit, we call that a junction or a node, the total amount of current flowing in has to be exactly equal to the total amount of current flowing out.
And this makes it crystal clear. If you've got currents I1 and I2 flowing into that center point, their combined total must equal the combined total of the currents flowing out, I3 and I4. It's not a suggestion, it's a rule. But why?
Okay, this is the mental image you need to have. This is so important. A wire is not an empty pipe waiting to be filled. It's more like a pipe that's already jam-packed with electrons. The battery isn't supplying new electrons, it's just providing the pressure to get the ones already there moving. So the second you push one in, another one instantly pops out the other end. No electrons get stuck.
All right, so that sorts out the current. No lost electrons. But what about that excess energy from the battery we were wondering about? Well, that brings us to Kirchhoff's second law, the voltage law. And it tells us there's no leftover energy.
This one's called Kirchhoff's voltage law, or KVL. It says that if you trace any complete path, any closed loop around a circuit, all the voltage gains you get from a source like a battery will be perfectly balanced by all the voltage drops across components like resistors. It all adds up to a nice, neat zero. And just like the current law was about conserving charge, this law is all about conserving energy. A fantastic way to think about this is to imagine going for a hike. If you start at a certain spot, climb up some hills, and then hike all the way back down to where you started, well, the total elevation you climbed has to equal the total elevation you descended, right? You end up back at square one. Voltage in a circuit loop works exactly the same way.
So the key thing here is the battery provides the electrical pressure, the voltage, and all the components in that loop then use up that pressure, every last bit of it. You can't just have extra voltage sitting around with nowhere to go. The circuit just naturally balances itself out.
Okay, so these laws seem pretty unbreakable, right? They're fundamental. But remember that question we kicked things off with? This is where it gets really interesting.
Let's ask it one more time. Are they ever wrong? And the answer is, well, it's kind of yes and no. It's more accurate to say they're an incredibly precise approximation that works perfectly under a specific set of assumptions. And this is the big assumption, the fine print, if you will. It's called the lumped element model. It basically assumes that for any single component, all the interesting physics, the electric and magnetic fields, are happening neatly inside that component. They aren't leaking out into the space around it.
The key factor that determines if this model holds up is frequency. For everyday DC and low-frequency AC circuits, this model is perfect. The laws apply flawlessly. But when you start cranking the frequency way up, we're talking radio waves, microwaves, those electric and magnetic fields just can't be contained. They start to radiate and interact, and that simple model breaks down.
And at that point, a neat circuit diagram starts telling you the whole story. The physical size and the layout of the wires suddenly matter a ton. To really analyze a circuit like that, you have to move beyond Kirchhoff's laws and into the much deeper physics of Maxwell's equations, actually simulating the fields themselves.
But let's bring it back home. Does this mean Kirchhoff's laws are wrong? No, absolutely not. It just means they're a brilliant and powerful tool that is perfectly accurate for its intended purpose. For pretty much all the electronics that power our world, from your phone to the power grid, these laws are the essential foundation.
So, at the end of the day, our puzzle is solved. Kirchhoff's laws are fundamentally correct, but understanding their limits reveals this whole deeper layer of physics. It makes you wonder, doesn't it? What other simple foundational rules in science have these kinds of fascinating exceptions hiding just beneath the surface?